Now, mostly in all the amplifiers, we will have this capacitance only appearing between input and output. We will not be having R and L. R will also come, but we'll ignore the R and we'll consider only the effect of capacitance, because the capacitive reactance is given by Xc equal to 1 by omega C, right? The capacitive reactance is 1 by omega C. At high frequency, as omega becomes very, very large, this reactance value becomes very, very small. It will behave like a short circuit. That is why we say at high frequency, capacitive effect is more pronounced. Inductive effect is less pronounced, because inductor or reactance is given by omega L. So as omega is very large, this omega L will tend to infinity. So it is just like open circuit. Open circuit the current will not flow, only voltage we have. But when you consider the effect of capacitance 1 by omega C, this will become zero. This will tend to zero. So if this goes to zero, it is like short circuit. In short circuit, very heavy current will flow and it will damage your device. So when you analyze the high frequency response of amplifiers, you have to give due respect to capacitance, because its effect is pronounced at high frequency of your amplifier. Okay, so if I have a capacitor CF, in this is in general we are saying, if I have a capacitor CF connected between input and output of my circuit, how am I going to decompose that? Okay, so the formula for Zi and Z naught. So write the formula for Zi. Zi equal to Z by 1 minus A. Okay, and the capacitive reactant is given by XCF equal to 1 by J omega CF. See, some books they include J in the reactants, some books they write JXC. So it depends on how we are going to analyze. Some books they write Xc as only 1 by omega C. Some books they write Xc as 1 by J omega C, as you see here. So it is all about logic only. Logically, if you are comfortable, both are correct. Okay, both are correct in their own ways. So logically, if you are correct, you can write in any notation, whatever you like. So the reactance is 1 by J omega CF. So at low frequencies, this reactance will become very large. It will be open circuit. So low frequency response, all these capacitors will be silent. In the high frequency, these the reactants will become very, very small. It will tend to zero, which means you will have a short circuiting effect. So if I apply Miller's theorem, I get at the input side Zi equal to Z by 1 minus A. I am applying this formula we have seen in the previous diagram. And Zi, so I am writing the capacitance as 1 by J omega CMI. CMI is C is capacitance, M is Miller, and I is input side. And Z value 1 by J omega CF into 1 minus A. So if you cancel the terms, you get CMI equal to 1 minus A into CF. So this is the value of the Miller capacitance at the input side. So CMI equal to 1 minus A into CF. Either resistance or how will the formula change? If instead of Z considering to be a capacitance, if I consider Z to be a resistance, what will be the formula? Can anybody say? I need answers from any of you. The capacitance, you get CMI equal to 1 minus A into CF. What will be the answer if it is going to be a resistance? Please attempt, and even if the answer is wrong, please say. We'll discuss it here. What is Ri equal to? What is Ri equal to? Should I call you by name for answering? What is Ri equal to? Rajeshwar? What is Ri equal to?